Okay, so the lecture is now being more populated, so we can start. So good afternoon, everyone. Thank you for being with us again in this celebration related to the women and girls in astronomy, or in general in science. And we are lucky today to have Dr. Randa Asad. She's from the American University of Sharjah. I believe I met Dr. Randa maybe 10 years ago, 11 years ago in Florida during one of those AAS meeting, the American Astronomical Society meeting. So it was a long time ago. So good that she is here at the American University of Sharjah. I believe she came here maybe 10 years ago, Dr. Randa, if you may correct,
yes.
10 years ago?
Yes, 2012, yes, 10 years ago.
Yes, great, yes. So she is an associate professor at the American University of Sharjah. She has been teaching, I believe, astrophysics. And she's very active in terms of galaxy research. And today she will tell us a little bit about what we call the chemical composition of galaxies. So please, Dr. Randa, you have the stage, inshallah.
Thank you very much. Thank you for organizing this event. And so today I'll be talking about science. So I'm going to be talking basically about the chemical history of galaxies. But I want to take this opportunity, as Dr. Elias said, that this is part of the events that are organized for the women and girls in astronomy. So I see that we have many girls and women here, and I hope that this is going to be like a motivational talk so that maybe they can get inspired, and hopefully they can, if they're interested in careers in astronomy, they can get some ideas. So I will be happy at the end when I'm done with my talk, if there's time, hopefully, if you have any questions to ask about this. But also I have to make sure that this is not only intended for girls and women, this is all for all type of audience. So everybody's welcome, and everybody's, I'll be happy to answer everybody's questions. Okay, so I'm going to share my screen. Okay, so I hope that you can see my screen.
Yes, we do.
Yes, good. Okay, so as I said, I'm going to be talking about the chemical history of galaxies. And because, as Dr. Elias said, most attendees of this talk are students, so maybe they don't have a lot of background. They have some background about astronomy, but maybe not enough background to understand the research that I'm going to be sharing today. The first few slides are very introductory so that we can go slowly from the very basics to actual research that is being done in this field. Okay, so whenever we hear about chemical composition or chemical history of galaxies, the first thing that comes to our mind is the periodic table with all the chemical elements in it. And we wonder, is that related to what I'm going to be talking about? And why do we talk about chemistry in astronomy? So the question is a very good question. And the answer is yes, we are going to talk about some of these elements. And the reason we talk about them in astronomy is that in chemistry, we talk about the applications of these elements and how what the properties are of these elements and so on. But there is a more fundamental question that we can ask, which can be answered through astronomy. The question is, what do we know about the chemical composition of the universe? So we see that now we're going on a much bigger scale. We're talking about the universe as a whole. So what we know so far is that the universe, our universe, started with a Big Bang. And at the time of the Big Bang, the first generation of stars had the chemical composition of about 75% hydrogen, 25% helium, and a very, very small fraction of the lightest elements. So if I go back to the periodic table here, you see that after hydrogen and helium, we have these three lightest elements. And those were the only elements in the first generation of stars after the Big Bang. However, if we look at the composition of galaxies that are being formed now, so more recent galaxies, the composition is different. We find still 75% hydrogen, that's the most abundant element in the universe, but now we have about 23% helium, and the 2%, that extra 2% is now for all the remaining elements in the universe. As you can see, two things changed from the time of the Big Bang. One is the composition, the actual elements that we have. Initially, we only had the very light elements. We didn't have, for example, iron, calcium, magnesium, and so on. And also the percentage. Initially, it was a very, very tiny, small fraction, but now it's about 2% of the composition of the universe. So then the question becomes, what caused this change in the chemical composition, and where all these new elements come from? Because now we're talking about periodic table. Back then, of course, there were no people to talk, but if they were talking, they were only talking about a couple of elements. So the question is, where did these elements come from? And the answer for that is stars. So I'm going to be talking a bit about how the stars form, how they're created, how they evolve, and then how they're going to enrich the interstellar medium between these stars. So at first, as you can see, so here, this is a picture that has many stars, but in addition to stars, there is also dust between these stars and what we call the interstellar medium. Out of this interstellar medium, there are some regions, as we know from physics, that because of gravity, things will collapse. So there are regions that are more massive than the others, and that causes these regions to collapse, forming new stars, as you can see in these two pictures. And then after that, so of course, I'm talking very briefly about this, but this is a long process and there is a lot of equations that we would have to solve and so on. But in very short terms, after a star is formed, there will be the first phase of the star would be what we call the main sequence phase. And that is the phase actually in which our own star, which is the sun, is currently in. And that is the phase where the star is fusing helium in its core. And because of this, there are two forces that are equal to each other but in opposite directions, which keeps the star stable. Those two forces are gravity inwards and pressure outwards. And as long as the core of the star is fusing hydrogen into helium, this is how the star will live or will look like. But as we know, the amount of hydrogen in the core of the star is not infinite. At one point, sooner or later, it's going to run out. And that's going to cause now the different phases that the star or the sun in our case, but any low mass star will have the same life, which is that after it runs out of hydrogen, it's going to expand. Now the pressure that was initially there balancing gravity, the pressure will be dominating, pushing the outer layers outwards, and the gravity will be contracting the core inwards. So now we will have two parts. And that's why, because of the pressure that's happening to the outer layers, we will see what we call a red giant, which is much bigger than the initial, the size of the initial star. But then, because the core is shrinking now, as it's shrinking, we know that the pressure is going to increase and the temperature is going to increase. So as a result for that, the core will reach the temperature needed to fuse helium. Because if you remember, I said that initially hydrogen was fused into helium. Now the core is made mainly out of helium. So this helium is going to start fusing when it reaches the needed temperature. So after that, once the core runs out of helium, the same thing will happen. Pressure is going to push the outer layers outwards, and gravity is going to make the core smaller, so it's going to shrink it. But the thing is that the difference here is that when helium is fused to carbon, the star after that will try to shrink the core more and more, but it will never reach the temperature needed to start fusing carbon. So it's going to be a core made of mainly carbon and traces of oxygen, and that core is going to be the end of the life of that star. So it's not going to go any further. So what's going to happen is that core is going to now become what we call the white dwarf, and the outer layers are going to expand peacefully in the outer space. So no explosion, nothing fancy. And that's going to be the end of the life of our sun or any low mass star. Okay. Now, the important thing to note here is that the star, regardless of its mass, is going to spend the longest phase of its life in what we call the main sequence phase, like the phase of our own sun. And that, once it runs out of hydrogen in its core and it starts doing all the other phases that I mentioned, those are going to be much faster, and then eventually the star will reach the end of its life. Just a note, I should mention that like the copyrights of these figures, these are not figures that I made. Some of them are from textbooks, some of them are from other sources, so just I should mention this. Okay, so now that we understood what happens to a low mass star, the story is the same for a high mass star in the beginning, when we said that hydrogen is being fused into helium and then helium into carbon. But because the higher mass stars will have more energy and more heat, the sequence will continue. So the star will not stop after carbon. As you can see in this figure, it's going to go from one element to the other until, of course, the list is longer, but this is just a rough sketch, until eventually it reaches iron. Now, iron is special, different than all the other elements, because iron is the most stable element, and it cannot fuse like other elements. So what will happen is that the star will not be able to sustain itself anymore when it reaches iron. So as a result for that, it's going to explode. And that is what we call the supernova, the core collapse supernova, which is the explosion of a high mass star. And as you can see here, again, as I mentioned earlier, the longest phase is the phase of burning hydrogen, which takes about 7 million years. As we go from one phase to the other, you see that things are happening faster and faster and faster. And then the last phase is very short. So as I said, the final stage of this type of star is a supernova, where an explosion happens. The ultimate outcome of this is going to be either a neutron star or a black hole. And I know that these are fancy topics that many people want to learn about, but unfortunately, we will not be talking about them in this talk. What I care about in this talk is the actual supernova, because if you remember, my goal is to discuss how the chemical elements of the galaxies change with time. So when a supernova like this happens, all the elements that were created in this star through its life, now they're going to be spread in the interstellar medium that's around it. And that's where these elements are coming from. So next time when new stars form, if we go back to the same story that I started with, when new stars will form from the interstellar cloud, now there are new elements that didn't exist in the original interstellar cloud. And that's where these elements come from. And one generation after the other is going to enrich the interstellar cloud more and more and more until we reach the chemical composition that we know today. So if we want to summarize this, I have a picture that summarizes all this. So here we see the different stars that form from an interstellar cloud. You see that the difference between them is in mass. The main characteristic that determines how the star will live its life is the mass. We start with let's start with the higher mass stars. So the highest mass stars will end up as black holes, and some of them will end up as neutron stars. And what we care about here is the supernovae that come out of these, because as we said, those are going to enrich the interstellar medium with new elements. And then the low mass stars will end their life as a white dwarf, and the way it's going to eject its material into the interstellar medium is by the planetary nebula. So if you understand these 2 points, now you can see that from an astronomy point of view, so far we have few elements that we care about. One is hydrogen, which is the most abundant element in the universe. The second is helium, which is the second most abundant element, and iron, which causes the star to explode. So we call it the star killer. And everything else, and this is an interesting way to look at it, that everything else in astronomy is called metal. So for example, even oxygen and other gases are called metal in astronomy because that's how we deal with them. Okay, now there is another way that some stars end their life. The reason I'm mentioning all these types of ending the life of stars is that each one of these ways will enrich the material around the star with new elements, completely different elements. So the other type that I would like to talk about is what we call the supernova type A, which is the result of 2 low mass stars. And as I mentioned before, based on the initial mass of the star, they will have different times to go from one phase to the other. So when we have 2 low mass stars, one of them might have become a white dwarf before the other one. So the other one is still a red giant, and the first one is now already a white dwarf. The red giant, as you remember, I said that the outer layers are being expanded in the outer space. So what happens is that because the white dwarf has more gravity, it's going to start pulling material for the red giant. And it keeps pulling material, as you can see here below, it keeps pulling material more and more. But of course, it's going to reach a limit that it cannot take anymore. And as a result for that, it's going to explode. So here again, this is an explosion, and that's why we call it supernova. But this is a different explosion than the initial one. The initial one was a result of a high mass star. This is a result of a binary system where the white dwarf was trying to accumulate more and more material. So a result of this, the reason why it's important to see the different types of how the stars will end their lives is that each one of these stars will have different lifetimes. If you recall the two slides that I showed you before, the low mass stars will live longer, which means that in order to have a supernova, which is a core collapse supernova, that's going to happen much faster, about 1 billion years before what we call the type 1a supernova, because as I said, the high mass stars die first. As a result for that, because each type of these explosions enrich the material with different elements, we will see that there are two categories. There is what we call the alpha elements, which are the lighter elements like magnesium and calcium and so on. Those are going to come into the interstellar medium at a different time than what we call the iron elements. So iron is one example for that, but they're the elements that are similar to iron. So let's keep this in mind, because this means that not all elements in the universe will appear at the same rate. They will appear at different rates based on the stars, the number of stars that die and their initial masses. Now, so because as we move, I'm going to be using the word metallicity. Metallicity comes from the fact that, as I showed you in that funny periodic table, in astronomy, we call everything other than hydrogen and helium, we call it metal. That's why we use the word metallicity to represent all other elements other than hydrogen. So hydrogen is given the symbol X, helium is given the symbol Y, Z is the mass fraction of all remaining elements in the periodic table. And of course, the sum of these should be 1, because that is unity, which means all the elements in the universe. And then there are some notations. I don't want to go through this because I know that most people do not like equations. But the idea here is that sometimes we roughly say that the metallicity is the same as the iron content, but that is not very accurate because, as we said, the different elements will form at different times in the history of the galaxy. Okay, so now let's start talking about something more practical. This was all some background that you would need in order to understand some current research that is being done in this field. So in order to understand the chemical history of any galaxy, we need two things. First, we need the high quality observations. We need to go to the telescope, obtain observations that are high quality so that we can analyze them. And then we need accurate theoretical models that can explain those observations. Because if I go to the telescope and I observe stars and I get results, but I do not know how to interpret these results, that's going to be useless. We have to have some theoretical models that have assumptions of how things are changing with time in terms of chemistry. But then I need observations to make sure that my models are correct, because otherwise you can make up any model and you think is right, but if you do not have evidence for it, it does not mean anything. And the best tools for doing this, and by the way, I should mention that I'm an observational astrophysicist, which means that I do the part about observations. I go to the telescope and I get observations of what I'm going to talk about now, which are star clusters. So the main topic today is to talk about the chemical history. So in order to talk about chemical history, we need two ingredients, the chemical composition and the age. Because history means that as a function of time, we want to see how the chemical composition is going to change. And that function of time is basically the age of the galaxy. And to do that, we rely on objects, astronomical objects that are called star clusters. And here are some pretty pictures of some of the star clusters that are out there in the universe. Star clusters are groups of stars that, as you can see in the picture, they're a group of stars, but they're not any random group of stars, but they are gravitationally bound together. So they're related to each other in the sense that they form from the same interstellar cloud. And as a result, because they formed from the same interstellar cloud, they have the same age and the same chemical composition. And that's why they are ideal to try to trace the chemical history of any galaxy. But now we start, so when we talk about these things, that all sounds nice and cool, but now we have to deal with certain challenges. One of the challenges is that we cannot observe any type of star cluster that we want. Some of them are too far from us. Some of them are maybe there is dust between us and them, so we cannot observe them. So I'm going to talk about two types of observations that help us identify the chemical history of the galaxies. And of course, the most logical thing to start with is our own galaxy. Let's say that I want to study the chemical composition and the chemical history of the central region of our galaxy, which is the Milky Way. Then I would be able to analyze individual stars in the cluster. Because I should go back here. If you remember these figures, if I can observe these clusters like they are shown in this figure, I can see the individual stars. So I take an observation of this star, this star, this star, this star, this star, and then I can make conclusions about the star cluster. However, if this star cluster is very, very, very far away, I cannot resolve the stars in the cluster. So I would have to take only one observation of the entire cluster. And that's what is called here integrated light. So first, I'm going to talk about analyzing individual stars in the cluster, and then I'm going to talk about integrated light. So I have to acknowledge my collaborators. The project that I'm going to discuss now is a project that I worked on in summer 2019, and it was published in 2020. This is done with collaborators from ESO and other institutes. So the idea is that there are some star clusters that were recently discovered in the central region of our galaxy, but there is a challenge that prevents us from observing these star clusters, which, as you can see here, and this is a real picture, the center of the galaxy is this bright region here in the middle. But as you can see, between us and that bright region, there is a lot of dust. So I cannot just put my optical telescope, which is the normal telescope that we're familiar with, and try to get observations, because I'm not going to get any observations from there. What I need to do is to try to, okay, just skip and then come back to this. What I have to do is to look at another wavelength other than the optical wavelength. So what we know is that dust scatters light, and the scattering, that's why we need to rely on infrared observations when we want to study the central region of our galaxy. So that is the first challenge. Challenge is that although we are still talking about the same galaxy, our own galaxy, that means that we cannot see all the individual stars in that star cluster, yeah, and we have to rely on red supergiants. As you can tell from their name, red supergiants mean that they are very massive stars. So first of all, they are evolved stars. They left the main sequence. As you remember, we said that first a star starts as a main sequence, and then it evolves. So those are already evolved stars. They have huge masses, between 10 to 30 solar masses, which means that they're 10 times to 30 times more massive than our own sun. And they are the largest stars in the universe. And that's why now it makes sense to you why we are going to focus on these in our observations. Because they are the largest, that means that they are very bright, which means that we can see them with our telescopes. And another thing is that they are young, so they're less than 50 million years. So this is also another important thing. It tells us about the recent star formation events that are happening in the central region of our galaxy. So we know that our galaxy is old, but this is a way or a proof that there are still stars being created in the central region of our galaxy. Okay, so for this project, we obtained infrared spectra with the VLT telescope. This is the largest European telescope in the Southern Hemisphere. It is located in Chile. And using these observations, so when I say observations, I mean spectra. So when we observe the spectra of these stars, we compare them to theoretical models. And by doing that, we can obtain different parameters of the stars. For example, as you can see here, for example, the effective temperature, which is the temperature of the surface, the metallicity, which I mentioned initially, that it can be assumed to be the content of iron, and so on. So the radial velocity and other parameters that we can get from the spectra. So using these parameters, we can extract, so those are just tools to help us understand the chemical composition or the chemical history of that region of the galaxy, because using these information, we can get the age, so temperature and the luminosity can give us the age of the cluster. And also by getting the metallicity from the spectra, we can know the chemical composition. And if you remember, I said that these are the two components that we need in order to understand the history, age and metallicity. So this is how we do it for the nearby stars, star clusters, where we can resolve the stars and we can get individual spectra of each star. Now, an ideal scenario would be that we observe the entire region of the galaxy and we make a map that shows the composition of different regions in the galaxy. Here, I'm sharing some results from other groups. You can see that this is a more recent paper. It just came out recently, a couple of months ago, about theoretical work that predicts the metallicity of different regions in the Milky Way. But to do that, to confirm these results, that's why we need more and more observations to make sure that these predictions are correct. And that's the aim of our project in this direction. Okay, but now the problem becomes harder when we want to go beyond the Milky Way. So I said that the Milky Way, we can look at the stars inside the star cluster and study them and get results. However, as you can see here, if we just go a little bit further, we have what is called the local group. So it's a group of galaxies that are the closest to our own galaxy. And we start trying to analyze star clusters in these galaxies. So the one that I'm going to discuss now is a galaxy that is called the Large Magellanic Cloud. As you can see here, there are two Magellanic Clouds near our galaxy. One is called the Large Magellanic Cloud, the other is called the Small Magellanic Cloud. So the remaining part of my talk is going to be about the Large Magellanic Cloud. And to do that, as I said, because we cannot see individual stars in the cluster, we would have to rely on the integrated light, which means that I take one observation of the entire cluster rather than looking at stars inside the cluster. And for this, I have to acknowledge my collaborator at Harvard Center for Astrophysics. This is a paper that we published in 2018. And currently we are working on a follow-up on this project, and hopefully we plan to submit the work soon. So the idea is that because the Large Magellanic Cloud, so again, this is the Large Magellanic Cloud, and this is another image of the Large Magellanic Cloud. Because this is a nearby galaxy, we can use it as a laboratory to test our new theories. We want the question that we tried to answer through this publication or through this project is to see if we can use integrated spectra of star clusters to trace the chemical enrichment of the Large Magellanic Cloud. Because if we can prove that it's correct for the Large Magellanic Cloud, which is one of the closest galaxies to us, then it's going to be possible to apply it to further galaxies. So for that, we obtained 15 star clusters as observations to test our models. 11 of those were observed with the SOAR telescope and 4 of them with Magellan telescope. So there are 2 different telescopes, but both of them are in Chile. And here are the results that we obtained. So age of the star cluster and the metallicity or the iron content of these star clusters. And using those, here are the exciting results, is that we tried to see if we can use these results to reproduce what the models are expecting. So in this figure, I'm gonna try to explain it. So here we have the chemical composition as a function of time. the red line here, the red solid line, this is what the model is predicting. This is how the model assumes that the composition, the chemical composition changes as a function of time over the years. Make sure that, so note that this is the log of the years. So this is like the giga years and million years and so on. It's put in a log format. So the idea is that the model is showing the prediction in the red line. The errors are the upper dotted line and the lower dotted line. And all these points that we see, the blue and green points, are our observations. There are two colors because, as I shared, those are coming from two different observing runs. But the conclusion of this is that we can nicely reproduce what the models expected. So the models expected this is how the chemical composition changes with time, and our observations were able to reproduce that. So this means that for faraway galaxies, for which we do not have models yet because we do not have enough information about, we can safely use this method. We go to obtain observations, find the relation between metallicity and age, and then we can come up with theories that explain the chemical history of those other galaxies. Now, so that was the general metallicity, like the overall chemical content. But now, as we said before, I mentioned earlier that the alpha elements, which are the lighter elements, will form at different time compared to the iron peak elements. And we can also show, this is what this figure shows, is that we can also show that the iron content alone of this galaxy, the model of it matches our observations. So the model is the blue line and our observations are the blue dots. And for the alpha elements, the green line is the model and the green dots are our observations. So we can see that our observations again can reproduce those two sets of elements. So the paper that we published had two main conclusions, is that this was the first evidence that we can use integrated spectra of star clusters to reproduce the chemical enrichment history. And the reason, so it was mainly one conclusion, but the reason this is significant is that we can now apply it to further galaxies for which we do not really have any knowledge about, and we do not have any models. After that, so after we finished this work, we obtained even more star clusters. So about 37 star clusters were added to our sample. And here I'm sharing some results that are still in progress. We did not publish them, but those are recent results that show the relation for the bigger sample that now we have, the overall chemical composition over time. So those are very good matches. We're still investigating to see what's going on with this cluster, but overall this is a good match. And the same is true for the alpha elements versus the iron content. So this is one of the conclusions of our new work. As I said, this is new, we did not publish it yet, but hopefully we aim to submit it soon. Now, the last thing that I want to share is these are results that we already submitted. This is another third project in which we look at the detailed chemical abundances of star clusters in the Large Magellanic Cloud. So first, we looked at the overall content, the overall metallicity, and then we split them into alpha elements and iron elements. And then the last thing, the most recent thing that we did is that we looked at individual stars, so individual elements. So here you see iron, calcium, magnesium, titanium, and so on. We were able to obtain the values for these for certain star clusters, and we plan in future work to add it to more clusters. So that's how we start. Like we start with the overall metallicity and then slowly go to individual elements. And our ultimate goal is to reach the periodic table that I shared in the first slide and try to see the chemical composition of different galaxies in terms of the elements that we know in the universe. So the conclusion for my work is that the chemical composition of a galaxy is enriched with time, which means that the chemical composition that we had back at the time of the Big Bang, or maybe like many millions of years ago, is much different than what we have now, and it's different than what we will have in the future. The chemical composition changes with time. Star clusters are very interesting tools. We saw that they're very pretty things in the pictures, but they're also very important tools that help us understand the chemical history of galaxies. Because of the large distance between us and the center of the galaxy, as well as the dust, we need to study the brightest stars in galaxies when we want to find the chemical composition. And also because of the scattering that happens because of that dust, we have to, instead of using optical spectra, we would have to use the infrared spectra. And then finally, for faraway galaxies beyond our Milky Way, we need to rely on integrated light, because then we will be able to obtain information about the star clusters, even if we cannot see the individual stars in the star clusters. And then the last point is that both theoretical models and observations are needed to be able to understand the chemical history of the galaxy. So that's an important point. So for me, as a observational astrophysicist, I get these observations, but I need to compare them with models. And the same is true for people who are doing mainly theoretical work, where they try to come up with new theories. They would need observations to test that their models are correct. So that's why without these two components, we will not be able to get new information about the chemical composition and history of galaxies. Okay, so that's it. Any questions?
Very much. Thank you very much, Randa, for this very nice lecture. I believe my student will find it very, very useful when we go into chapter 9, which is deals with stars formation, black holes, neutron stars, white dwarfs, supernova type A, type 2. So thank you very much for this. So let me open the floor for any questions for the students. I believe there was one question as a chat, if you can see it.
I'm checking it now. Okay, yeah, so I think the first question is, how did we know the available elements after the Big Bang? Yeah, this is a very interesting question. So something that we can, maybe I should have mentioned this when I explained it, is that when we observe different stars or different star clusters, is as if we're going back in time. So there are stars that are all as old as the universe. And when we study those stars, we can basically trace what was the chemical composition back at those times. And that's why it's important to when we want to know the chemical composition of a star or a star cluster, it is very important to know what is the age of the star, because then it tells us the chemical composition at that time in the history of that particular galaxy. Okay. Yeah, is it true that iron in Earth came from the stars, and does that apply to other elements? Yes. So this is so if this is a student, I think you will learn this in astronomy. So our solar system is so let's talk about our sun. So our sun and the entire solar system is a young star, which means that it formed recently. So it formed the sun and the solar system from the leftovers of previous generations of stars, as I explained. So stars die and then new stars form. So our solar system formed or was created out of this specific composition. So all the elements that we have here on Earth are, it is true that they are coming from the leftovers of dead stars from before. So yeah, that is correct. Yeah, and it does apply to every element. Yeah. Oh, sorry. So I saw Dr. Elias, you answered that. Yeah. Sorry.
There's a question. Which theoretical models you use? There's a question.
Yeah, so I see this question. What is causing the enrichment of the chemical composition of the galaxy? Yeah, so what causes the enrichment is the stars. So so there's a term that we call the star formation rate. The higher this rate, the more stars we have, the faster the enrichment happens. Because then we have many stars, they will live their life, and then they're going to enrich the galaxy at the end of their life. Because if you remember, I showed you how the different elements form in the history of the star. But then all these new elements will be returned to the interstellar medium when the star explodes or when it dies. How do you get the, yeah, so how do you get the infrared spectra? So that is from, I use the VLT telescope. With the VLT telescope, you can get different ranges, like different wavelength ranges. And what was used for our analysis is the infrared part. And of course, that's not possible with all telescopes. Certain telescopes are sensible or sensitive in the infrared, so you can use them, but other telescopes are not. So this can be only done with certain telescopes.
There's a question before, which theoretical models you use?
Which theoretical, yeah. So I use, so because I shared different things, so I don't know if it's a technical question. A technical answer is that for the red supergiants, I use the Mark's models. For the one that I showed, the red line, this is a model introduced by Spitoni et al. In their 2017 paper. And what other models did I use? Oh yeah, I think those are the two ones that I shared in my slides. So those are, so when I use theoretical models, I just search the literature for the latest models and try to apply them. Any other questions? Oh, so are there any observation evidence for the existence of population-free stars? I think there are some papers that say that there are some population-free stars, but in my work, like in the star clusters that I observed, I have not seen any. But I think there are some papers that talk about the evidence for these stars. Mm-hmm.
So this was a question from a good friend, Dr. Walid Azzam. He is in Bahrain. So good to hear from him.
Yes. I know him, yes. How are you, Dr.
I have a question, Dr. Randa, about the advent of this new telescope, the Vela Rabban new telescope. Will it be possible to get detailed observation of, let's say, M31 and what you are doing?
Yes, we are hoping so. So the problem, so we have two things. We have to have like the larger telescopes, but we also need to have like very good spectrographs so that they can give us a very high resolution. Because sometimes there are large telescopes that do not have sensitive spectrographs for this work, so then it cannot be used.
Another question for you?
Yeah, so yes, I did. Yes, so about the iron in Quran. Yes, that is right. And that's actually, because it was mentioned about the Holy Quran, I want to mention something. So when I teach astronomy, when I talk about the chemical enrichment and the fact that our Earth is made of elements that come from other stars, sometimes students say, like, astaghfirullah, like, no, this, we don't want to believe this. But in fact, so even the elements in our bodies, if we believe that they are from elements that come from stars, I don't see any contradiction between our beliefs in Islam and what we know from science, because we know that we are made of dust, and this dust is the dust of Earth, and Earth, according to science, is the result of the stellar, the elements that come from different stars. So yeah, so I think, I mean, we can discuss this. Maybe, I don't know if it's like, if anybody wants to discuss this, I just want to make sure that it's not something, nobody thinks that I'm saying things against what is in the Quran.
So Dr. Randa, for the last question, what do you advise for female students to pursue or to follow science majors or engineering majors and so on? So what do you advise them using your own experience?
Yes, good question. So first, the general answer is that, so sometimes we push people to do science or astronomy and things that we like. But before I have two pieces of advice. The first one is for people who want to do this and they are not confident enough, or they are worried that they cannot succeed. But then I will have a general advice to people in general. So I'm going to start with the first one. So the first one is that if you like the subject, and if you think that it's going to be a long way or a difficult journey, my advice is that as long as you like it, you will enjoy it, even if it's going to take a long time. So usually, like, for example, if you want to have an academic path, so you start with undergraduate and then you do your PhD and so on. So that's, I have to admit, it's a long journey. But in my case, because astronomy was a subject that I really liked, so it was my choice from the beginning, I never felt that, oh, this is taking me so long to, for example, graduate or to get my PhD or anything like that. I was enjoying it as I was progressing in it. So if you like it and if you enjoy it, even if you think that you need to learn a lot, yes, it's going to require a lot of work. It's going to require a lot of dedication. But the main thing is that if you like it, you will be able to succeed, inshallah. And the other point is that just to make it clear, because sometimes I might sound that I kind of like push everybody to study astronomy. That is not right, especially for women and especially for our culture. Success, from my own point of view, is not in one path. So in order to be successful, you do not have to be an astronomer. You do not have to be a scientist. You do not even have to get your higher degrees. You can be like a stay-home mom and be very successful at your house, and you're still counting as successful. So that's why just, it depends on what you like. If you like this path and you want to try it and you enjoy it, go for it. If not, just think about what is the ideal life or ideal path that you would like to have, and make sure that you do it the best way you can, and then you will be successful in that area.
Thank you very much for these advices. One last question from Mohammed Ataf. You can read it so that we close.
How can you determine the age of the universe, considering that twilight? So mainly, yeah. So in like the quick answer for this about the age of the universe is that yeah. So based on the law of expansion of the universe from Hubble law, we can use the details of this to get an approximated age of the universe. So of course, the more accurate observations we have, the better we get the final result. But for now, we have, that's why we always call it the approximated age of the universe. We do not have like the exact age of the universe in minutes and seconds and so on, but roughly we have an idea about the age of the universe from Hubble's law.
Thank you very much, Dr. Randa, for this very nice presentation, and also for all the nice advice that you have sent to our students, and hopefully they will follow your path. As you said, not to be necessarily an astronomer, but or a scientist, but to be just a person that does love what she does and so on. That's very, very important. So we thank you again for this presentation, and hopefully we can have you more in the near future. So we are very grateful to have Dr. Randa. She is participating with us in this Women and the Girls in Astronomy. She is a professional astronomer by birth, I can say, so to be much, much better to say it, because what you do is a vocation and you love it, and that's why you are so successful. Thank you again, Dr. Randa. We see you next time, inshallah.
Thank you so much. Thank you.
Thank you. Thank you. Thank you. Bye. Assalamu alaikum.